Okay, so today we're going to review the circle to start. So I don't know, but when I took calculus, I did not know where those numbers in the unit circle came from. Anybody else feel like that? Ish, tad. Okay, so the first principle that they come from is they come from two special triangles. So the first triangle is a 45, 45, 90 triangle. And I think everybody remembers enough geometry to know that if this angle is 45 and that angle is 45, that one has to be 90 because the angles add to 180, right? And if these two angles are equal, these sides have to be equal, right? That much is easy enough. How do you think they prove that this side is root 2 then? Yeah, a squared plus b squared is c squared, right? So 1 squared plus 1 squared is c squared. 2 is c squared, therefore c equals root 2, right? Now, how this translates to the unit circle is in the unit circle, you draw little triangles whose hypotenuses are 1. So I take this triangle, and I want to scale it down, so its hypotenuse is 1. So how could I multiply this by a scale factor and shrink it? What would that scale factor be to make the hypotenuse 1? Divide by root 2 everywhere. Does that make sense? And that preserves the angles and the relationships, right? It just makes it smaller. So imagine that it just shrunk. And so root 2 over root 2 is 1. 1 over root 2 you more commonly see as root 2 over 2, right? When you rationalize the denominator. Do you guys understand that? By multiplying this by root 2 over root 2.
It's kind of pointless, but
Yeah? Good?
Huh?
Say that again?
I think it's kind of pointless.
To rationalize the denominator? Yeah, I think the only reason to do it is really to have like some consistency and to know when two things are equal. Like, so you can easily compare answers, but I mean, like, I don't really care if you leave it as 1 over root 2. It's just that it's more often given as root 2 over 2, so it's good to know that that's the case. Yep. Okay. So that's where the first triangle comes from. Just keep that in mind. The second triangle is a 30, 60, 90 triangle. So how you produce that triangle is you begin with a triangle that's equilateral. And if it's equilateral, what are all of the angles? And they're specifically what number? 60. Okay, so every angle is 60. And then you just say, okay, I'm going to make all the sides 2. You could do that with any number, but they're all going to be 2 for now. And then you take the angle up top and you bisect it, as in cut it in half, which makes it 30, and makes this right triangle. Does that make sense? And because you bisected this angle, you've also bisected that lower side. So since the side from C to B was 2, D to B has to be 1. Does that make sense? And this side you just assumed was 2. And so how do you think they found that that other side was root 3? But again, yeah, you would do 1 squared plus b squared equals 2 squared. So b squared would equal 3, and b is equal to root 3. That's where that comes from. It comes from the Pythagorean theorem. It's your best friend. Now, how would you make this triangle so that the hypotenuse is 1? What would you divide by? 2. And so notice the side opposite the 30-degree angle is the half, and the side opposite the 60 is the root 3 over 2. And the hypotenuse is 1. Is everyone okay with those little triangles? Okay, we're going to use the little triangles right now, after I have some coffee. My coffee has cayenne in it this morning, so if I seem a little bit like hyper, that might be why. Okay, so now, the first thing with the unit circle is, do you guys know an easy way to count out all of the angles in radians? Because this is the first thing I think that we should make sure you can do. And here's my trick. I think it's a pretty good one. Count by quarters, and then count by sixths. Here's what I mean by that. So you know that the whole way around the circle is 2 pi, right? So what's this angle right here in radians? Pi. And what's the upper 90-degree angle? Half pi. And this one down here is 3 pi halves. Okay, great. Now, the red dot is halfway to pi halves, right? Which is pi quarters. So you see how it's a 1/4, 2/4, what's this one? 3/4. 4/4 is pi, this one is 5/4, 6/4, 7/4. And if you go bigger than 7/4, you just count by quarters some more. Does that make sense? Now to get the blue ones, you should count by 6. You see how the distance from here to here is the same as there to there, which is the same as there to there. They're each 30 degrees. So if that first one is 1/6, the next one is 2/6, and 2/6 reduces to 1/3. So there's pi thirds. So 1/6, 2/6, 3/6 is pi halves, right? 4/6 is 2 pi thirds. And then you've got 5 pi 6. 6/6 is pi. 7 pi 6. 8/6 is 4 pi over 3. 9 pi over 6 is this bottom. 10/6 is 5 pi over 3. And then 11 pi over 6. That isn't the only way, but that's a way that I think works out pretty well to count them. Does that make sense? Good, okay. Okay, now then the question is where do those numbers in that first ordered pair come from? And here's where. So draw a triangle. This little inner angle is 30 degrees or pi 6 radians. The hypotenuse, because you're inside of a unit circle, is 1. Exactly. And according to the triangles that we just drew, that means that this base side is √3/2. Does that make sense? And the other side is 1/2, right? And the coordinates of a point are, x is how far over, y is how far up, right? Now, if you revert back to your definition of right triangle trigonometry, so TOA, because if we'll remember it, right? Using that triangle, sine of that angle is the opposite side over the hypotenuse, so 1/2 over 1. Which coordinate is that in that ordered pair?
Y.
The y. Cosine is the adjacent side over the hypotenuse, right? So that's the other part. So this number is the cosine, that number is the sine. You see that? They're alphabetical. Cosine is x, sine is y. Someone was being nice. How about this next one? What triangle is that going to be? This,
45.
That's 45 degrees, and that's the 45, 45, 90 triangle. So what was the over side? What was the upside in that one? Or both of them? They're both √2/2. So at that angle, sine and cosine are both √2/2. And the last one, that is 60. If this is 60, those sides from the first triangle just flip-flop, right? Now the x part is 1/2, and the y part is √3/2, right? I claim that that's all you have to memorize, because once you have that, everything else is a reflection and paying attention to signs. So this point 2 pi thirds, that's this point at pi thirds reflected over, right? Does that make sense? You can get this by, it's sort of there's symmetry. This side is then a negative number, that side's a positive number, right? So what would the coordinates be at that point? So at that angle, what is the cosine? -1/2. And then what's the next point going to be? And then positive √2/2 for the y. And you kind of keep going like that, right? This next one would be negative √3/2, positive 1/2. What are the coordinates at pi? -1 and 0, exactly. And at pi halves, they're 0, 1. Here you're at 1, 0. And so that the idea that you generalize the quadrant 1 is right triangle trigonometry, and then you generalize that to angles where there are where they're too big to be triangles by saying, okay, well, if the sine is the y and the cosine is the x in quadrant 1, let's just keep that consistent in all the other quadrants. That's how you make this work for all sorts of angles. What would the coordinates be at 7 pi 6? Exactly. And this one's negative root 2 over 2, negative root 2 over 2, negative a half, negative root 3 over 2, right? That one is 0, negative 1. And in quadrant 4, the coordinates are positive a half, negative root 3 over 2, because the y is now negative, root 2 over 2, negative root 2 over 2, and root 3 over 2, positive negative 1/2. Last one got a little bit messed up, but you see the idea. I'm not going to ask you to like reconstruct this whole thing, but I'll probably ask you to find sine and cosine of a bunch of angles just to see if you can. Does that make sense? Okay. So my friend Bob also noticed that there's a pattern in the numbers and that they go 3, 2, 1, 3, 2, 1, which if you know that works for you, it's fine, but there's a reason they do go that order, and it is the triangles. Okay. So there's unit circle flash review. Now we're going to find sine and cosine and tangent and stuff and graph pictures and all sorts of fun things. Hello. Tell me your name. Mendez, thank you. Tate. Okay. So sine of negative 2 pi thirds. Look at that circle. Tell me what is the sine. What is the sine at negative 2 pi thirds? So negative 2 pi thirds is the angle that's right there, right? So at that angle, wait, that's wrong.
No,
It's this one right there.
yeah,
Yeah. Okay.
it's negative root 3 over 2.
Do you guys agree with that? You got a nod, or give me a thumbs up or something. Okay. Can't read your minds. I don't want to. That'd be weird. Okay. 11 pi quarters. So what's the biggest pi quarters you see on there?
I actually don't get it.
Yeah, we'll go back to the circle, okay? So look at your circle. That's the pi thirds angle. That's the 2 pi thirds angle, right? So negative 2 pi thirds is just the backwards direction. So same distance. Does that help? So that lands at this one, where there are 3 of them, is the first of the 3. And at that point, the x-coordinate is negative 1/2. The y-coordinate is negative root 3 over 2. The sine is the y-coordinate of that pair. That's all. Okay, looking at quarters, this angle that I drew is 7 pi quarters. So if you want to get to 11 pi quarters, just count by quarters. There's 8 pi quarters, 9 quarters, 10 quarters, 11 quarters. Does that make sense? It's the same thing as 3 pi quarters as an angle. And what were the coordinates at that point?
Negative root 2 over 2.
And then positive root 2 over 2 for the y, right? So this is equal to negative root 2 over 2. Three pi halves on the circle.
0.
That's this point whose coordinates are 0, negative 1. Cosine is the x. That is going to be 0. So on the unit circle, cosine's the x-coordinate, sine's the y-coordinate. Okay, we did this one yesterday, but let's just do it again. So use the unit circle to graph sine. So I'm going to call this endpoint 2 pi, this negative 2 pi. And if we're graphing sine, are we looking at the x-coordinates or are we looking at the y-coordinates? Y, yep. Okay, so beginning at an angle of 0, the coordinate of sine is 0. By pi halves, it's up at 1. Pi, it's at 0. 3 pi halves, we're down at negative 1. And 2 pi, we're back to 0. That's if you are to go in a counterclockwise, which is the whole positive direction business. So what happens at negative pi halves? Negative 1. Negative pi, you're at 0. Negative 3 pi halves, we're at 1. Negative 2 pi, we're at 0. Okay. All right. And of course, you know, the points like pi quarters, you'd plot by, like, say, taking root 2 over 2 and knowing it's about 0.7. You know, go over pi quarters up about 0.7. And you, at 60 degree or 30 degrees, you'd say, okay, well, that's root 3 over 2, which is, you know, ish, some decimal. That's why it gets the curvy shape that it has, because the specific value's at those numbers. That's why. It's not straight. Okay, cosine, same idea. But what coordinates do we use now? The x's, exactly. Okay. So what is the angle 0? X coordinate is 1. Great. Angle pi halves, x coordinate is 0. Angle pi, x coordinate is negative 1. 3 pi halves, we're at 0. 2 pi back at 1. And then repeat that in the negative direction. I'm not an English teacher, so I can say stuff like this. Wikipedia has a spectacularly awesome animation about this. Like, so they show like a particle going around the unit circle, and then they draw out the sine curve as it does so. It's pretty cool. So go to Wikipedia and just take a look at that. Math people are pretty like picky about stuff being right, so I'm sure some of them in their spare time like peruse Wikipedia and make sure things are correct, especially basic stuff like this. It's a good place to look for some demos and stuff. If I have time at the end, I'll pull it up. Okay, sine of 2x we kind of did yesterday, but we can do it again. So this is going to oscillate more quickly than the regular sine function, right? So how do you find the period? What do you do with the 2x? Is that equal to 2 pi? Exactly. So whenever that equals 2 pi is when it's done. So that happens when you equal pi. So if there's pi, it's 2 pi. And how many cycles will sine go through in 2 pi? 2, exactly. And sine begins at the origin. It's going to have to go up to 1 by pi quarters, down to 0 at pi halves, down to negative 1 at 3 pi quarters, and up to pi. So the whole entirety of that picture must take place in pi. And then just do it again. I really can't draw it without having the dots. Like, that's lame, but it's just... how it works for me. Okay. I think, is the next one cosine of x? Are you okay with the sine 2x, that it oscillates twice as quickly and same picture? Or same general shape? So if doing 2x made it go faster, what do you think x over 2 is going to do? It's going to slow it down. It's going to look like a long wave as opposed to like a hyperwave.
It's the same thing, x divided by 2 is equal to 2 pi.
Exactly, yep. And for sine and cosine, that's because their base period is 2 pi, so whenever your expression equals 2 pi is when that's done. So this is going to be x equals 4 pi. And if I make this 2 pi, like as in 2 pi is what's at my right half and negative 2 pi is my left end point, This also means cosine is going to go through half a cycle until 2 pi, as opposed to a whole cycle. Does that make sense? Okay. So where would cosine begin? It'd begin at 1, right? Now I'm just going to add in, I'll just put 3 pi, and I'll put 4 pi over there, and we can graph that whole thing. We're just going to ignore the part that we're drawing in extra. So it would begin at 0, at 1 at 0, and it would end at 1 at 4 pi. When's it going to cross the axis? It's actually going to cross it at pi. I think what you were thinking, it'd be negative 1 at 2 pi, right? Back to 0 at 3 pi. So that would be the whole cycle in 4 pi. But all you'd have to graph, if I said 0 to 2 pi, is just that first bit. But if it makes you feel better to graph the whole bit and then just erase it, I understand your pain. And then the rest of it just reflects over the y-axis, right? So that graph's going to cross the x-axis at negative pi and be down to negative 1 by 2 pi, by negative 2 pi. We briefly discussed even and odd functions yesterday, and we said that even functions have symmetry about the y-axis, right? Does it make sense that y equals cosine x is symmetric about the y-axis? Does that make sense? Okay, which means it is an even function. Does that make sense? And with even functions, when you plug in negative x, you just get back the original function, right? Okay, that means that cosine of negative x equals cosine of x. Because it's even, you just replace the f by cosine, by a specific function. That's an identity you maybe learned in a trig class, so you should have at least. What about sine? What kind of function is sine? Sine is odd, because it's symmetric about the origin. And if functions are odd, that means when you plug in negative x, the negative can pull out and multiply in front, right? Which means that sine of negative x equals negative sine x. And that's true because of the oddness. How so you justify negatives coming out of sines. If you take calculus 2, you learn you can express sine and cosine. Sine can be expressed as an infinite sum of things that are odd powered, and cosine can be expressed as an infinite sum of things that are even powered. So it's kind of cool. The other thing I was going to say is one way my AP Calc class was mean is they did one question on a multiple choice test in which the answer came out to be sine of, I think it was cosine of negative 2, but that answer wasn't listed there. What answer do you think was listed there? Cosine of 2. They had to recognize, oh, cosine's even, so cosine of negative 2 is cosine 2. That was a mean trick. But that's why you don't want multiple choice tests, because mean stuff like that can happen. Okay, and I made a bit of a typo here, but here's the old fix-it. So the other 4 functions, you really just have to know what they are. Tangent is defined as sine over cosine, which you also can define from a triangle, but ends up being sine over cosine. Secant is 1 over cosine. Cosecant is 1 over sine. And this last one should say cotangent, so it should say COT, not COS. So cotangent is cosine over sine. These last 3 functions are called the reciprocal. Does it make sense why? Because the reciprocals of things, right? The reciprocal of cosine, the reciprocal of sine, the reciprocal of cosine. I don't know why they didn't make these different. Like, why didn't they put the C one with the C one? I don't know, okay? That was stupid, but it just is what it is. So you have to live with it. Can we handle it? Probably. Okay, we're going to go with it. Okay, so the way to find values here is to revert back to what they are with sines and cosines. So tan of 3 pi quarters is sine 3 pi quarters over cosine 3 pi quarters. So you look at 3 pi quarters, which is that angle. Is the sine positive or negative? Positive. And it's root 2 over 2, right? The cosine is negative. Awesome. So that equals -1. Ah, rock on. Okay, cotangent of pi 6 is cosine pi 6 over sine pi 6. Ooh, okay. Test my circle drawing abilities. That first point, root 3 over 2, a half. So the cosine is root 3 over 2, and the sine is 1/2. And then the whole over 2's are just silly because they're both over 2, right? So you can multiply by 2, and gives you root 3. Okay. Secant of pi is 1 over. What is cosine of pi? Okay. Which is. Why did I just say 0? That was stupid. I don't know what happened. Do you ever write what you don't mean? -1. What if, just one more, let's add in. What if I'd given you cosecant of pi? That would be 1 over 0, which is undefined. There will be a vertical asymptote there of that function. Okay. No problem, not at all. Now let's graph tangent. No problem. All right, tangent. So start by just sort of putting like a little unit circle either in your mind or on your paper. So that's the point 1, 0, 0, 1, -1, 0, 0, -1. Okay. Remember that tangent is sine over cosine. And we'll call this 2 pi. Call that pi. -pi, -2 pi. Okay. So what is tangent of 0 going to be? 0. Because you take the sine divided by the cosine, in other words, the y divided by the x, right? 0 over 1 is 0. By that? 0 over 1. How many 1s in 0? None. What is this pi quarters? Is root 2 over 2, root 2 over 2, right? Tangent there is going to be 1. So this is pi halves. Halfway is pi quarters, then you're at 1. Can you do tangent of pi halves? It's an asymptote. And what's going to happen is as you get close to this asymptote, that triangle ends up looking like this. The y is getting close to 1 and the x is getting close to 0. What's 1 divided by a really small number?
Really big number.
A really big number. 1 divided by a million is 1 divided by 1,000th makes 1,000, right? So what happens to tangent there is it explodes. It goes to infinity. Funny story, there were some mathematicians discussing math before getting on an airplane, and they said, oh, if we do that, it's going to blow up the plane. They meant like the plane of numbers, not like the airplane itself, but yeah, great joke. Okay. And then if you go backwards in this direction, what's going to happen at negative pi quarters? What will the tangent be there? -1. And then it's going to do that kind of pattern. And that pattern is going to repeat. So, for example, at this angle, which is 3 pi quarters, you're going to have -1. By pi, you'll have 0. And by 3 pi halves, you have another problematic asymptote. So that little picture just tessellates. So tangent is 0 at all whole number multiples of pi. Does that make sense? Like 0, pi, 2 pi, 3 pi, 4 pi, right? And that'd be the whole picture that we had in our interval. What is the period of tangent? The period is pi. It has a shorter period than a sine or cosine function, right? You see that? Okay, so there's tangent's picture. Did I do logical and make cotangent next? Yeah, okay. So cotangent will be a little bit different because instead of being sine over cosine, it's cosine over sine. So this is cosine x over sine x. So same points, we got 1, 0, 0, 1, negative 1, 0, and 0, negative 1. So if you're doing cosine divided by sine, you're doing the x divided by the y, right? So can you do 1 divided by 0? No, so 0 is an asymptote, or the y-axis is an asymptote. How about at pi quarters? What is the cotangent going to be at pi quarters? 1. Okay. How about at pi halves? What's the cotangent going to be? 0, great. 3 pi quarters is this angle. What's it going to be there? Negative 1. And where is the next asymptote at? Pi. So it's the same picture as tangent except for like a little bit reflected and a little bit shifted. You see that? Okay. And then the same thing happens between 2 pi. You cross at the 3 pi halves and have the same general pattern. Ish. So what matters with those functions is that you can get the asymptotes in the correct place and you get the sort of general shape correct. Does that make sense as an idea? So this one has asymptotes at all the pi, all the whole number pi's, right? 0, pi, 2 pi, 3 pi, and all the negatives as well. And what is cotangent's period? Also pi. So you're figuring out how to compress like cotangent of 2x. You set 2x equal to pi instead of 2 pi. Does that make sense? So for example, if we had cotangent of 2x, that would go twice as fast as cotangent, right? And you'd set 2x equal to pi because pi is the base period of that particular function. Okay. I know it's fast and furious, but I can do. All right, secant. So secant is 1 over which function? 1 over cosine. So I think this is a brilliant way to graph these functions. First, graph the cosine function. My pre-calc book called that the guide function, which is graph cosine. So cosine begins at 1, crosses at pi halves, it's negative 1 at pi, crosses, negative 1, blah, blah. Okay. So there's the cosine function. I'll pause and drink coffee while you catch up. So from that picture, where is 1 over cosine going to have problems? Where it crosses the x-axis, because that's going to be where you're doing 1 divided by 0. Does that make sense? So wherever this picture crosses the x-axis, that means the cosine is 0, right? And 1 divided by 0 is a no-no, right? So wherever you have a cosine crossing the x-axis, your function is going to have an asymptote. So draw in your vertical asymptotes there. So vertical asymptote.
And everything else stays the same?
And we're not done with that yet, but we know this is the first step. Draw in the asymptotes. Because it definitely doesn't stay the same. Okay. But you get where the asymptotes come from. That part good? Okay. Now let's just look at the part of the picture that's just right here, the part in the middle. This is 1. 1 divided by 1 makes 1. So that point stays the same on your secant graph. Now, this part here, what's happening to those y values as you approach that asymptote? They're getting close to 0, right? They're getting small. What does 1 divided by a really small number make? Really big number. So what happens there is when you do 1 divided by the cosines, the results get larger and larger and larger until they approach that asymptote. Like this number you're doing 1 divided by is like 0.1, 0.001, 0.0000000 gazillion O's in a 1, which makes it huge. And then what do you think happens on this side? Exact same thing. So that picture ends up looking like this. I mean, you could think at one point in time the cosine is 1/2 and 1 divided by 1/2 is 2, right? Which means that y value of the secant function goes up to 2. But the point is the values of cosine decrease, so 1 over cosine increases. How do you think it's different from this little part that's down here? Because the general shape of this is the same, right? But the difference here is those y values of the cosine are negative. So if you do 1 divided by a negative number, it's just negative, so it's going to look like this. And the same thing over here to look like that. And they're kind of parabola-ish shaped in the middle, but not really be parabolas because parabolas don't have asymptotes. So parabola-ish, I think, is the way to describe it. So the black part isn't actually the graph of the function. The part that's the graph of the function is the purple thing. The black part lets you get the purple thing. And for me, it's the way that makes the most sense. It's kind of weird, but what is the range of secant? Exactly. See, it's missing all the values in between -1 and 1. It's kind of like the anti-cosine, right, in some sense? Okay, so that's how you do secant. How do you think you graph cosecant? Almost the exact same way, right? So graph the sine function, try to do the same thing. Just give it a shot. Like, I'll do it too, but I'll try to slow down and drink coffee before I start. The picture,
The parent function thing works pretty easy.
It is pretty nice, isn't it? It's pretty slick. The whole like guide function thing is pretty cool. It's almost the exact same picture except for it's moved over, right? Just like sine is the translation of cosine, cosecant is the translation of secant, right? I mean, it's a shift and maybe a flip or something. But yeah, I didn't learn that guide pair and trick until I read a pre-calculus book, and I was like, oh, that's how you graph things. I learned it when I was in high school and then promptly forgot it. Or I was absent that day and didn't learn anything, which happens all the time. So hopefully that helps you at least know a way to find that. Okay, I said to graph here, but I'm going to override my own ruling, and I'm going to tell you to use an identity to solve this. And there are not very many trig identities that you have to know in this class. I can think of 4, maybe 6 if I push it, okay? But one that's useful to know is a little bit specific, and it's that sine of 2x is 2 sine x cosine x. And I'll try to not have it come up too often because I think there's just so much you have to memorize already. But that is one of the double angle identities, and it is one of the more useful ones, so it's good to know it's one that's going to come up. It comes up in calculus 2 as well, so I can tell you it with certainty. And how that's helpful is you can say, well, solving sine x equals sine 2x is the same as sine x equals 2 sine x cosine x. Has everyone okay with that part of it? No, I know this is an identity that you were supposed to have learned at some point in time. There is a reason that is true, and it's long and complicated, and I can't go through it now. Okay, like it's not because I don't want to, it's just because it takes forever.
How is sine x equal to sine 2x?
Oh, we're just solving that equation. So we're saying, like, when does this happen?
Oh.
So like, if you were to say, like, graph sine x, which would look like, I can do it really quickly, you don't have to, but here's what it would look like. Wait, crap, did that backwards. I should not do stuff fast. So that's regular sine x, right? Sine 2x goes twice as fast, right? So it will look like that kind of thing, right? Does that make sense? And the question we're asking is, what are those intersection points? Does that make sense as an idea? Like, where do those two graphs, at which angles do those two graphs cross each other? And because of our inability to draw super well, I mean, I'm sure you guys are not all that different than me. Drawing's hard, right? It's hard to figure out where they are exactly, but they do obviously cross a couple of times, right? And so one way to solve that algebraically, which definitely is the way that I prefer, is to use this identity. So I guess what your question was is that, okay, well, sine x doesn't equal sine of 2x all the time, right? But the question is, when does that occur? Does that make sense? Kind of like x squared doesn't equal x all the time, but you can figure out where they are the same, right? Okay, so if you were solving something like this, why can't you divide by sine? Why is that a bad boo-boo? It might equal 0, and division by 0 is not okay, right? So you can never divide by crap that's got variables in it, because the stuff could have been 0, you just don't know. So don't divide by variables ever, bad. Okay, but you could instead take away that sine x and say, well, 0 equals 2 sine x cosine x minus sine x. Is that okay? And then you employ your awesome powers of factoring and take out the greatest common factor. What is the greatest common factor on the right-hand side there? Sine. Good? Is that okay? And then you say, okay, well, I can figure out where does 0 equal sine, and where does 0 equal 2 cosine x minus 1. And you're going to have to solve equations like that in this class all the freaking time, so it's something we know how to do. So you look at your unit circle, and you say, okay, the first part. Where are the signs equal to 0? 0, 2 pi, 3 pi, etc., right? So if x is equal to 0, plus minus pi, plus minus 2 pi, to put that into WebAssign, you're going to have to say x equals pi n, where n is an arbitrary integer. So those are all the places where sign is 0, and you can see that in the picture that we're having these things cross at 0, pi, 2 pi, right? Those you can kind of see that they're happening. Are there more intersection points? Yeah, so you solve the second equation, which is the same as saying cosine x equals what? 1/2. So cosine will be 1/2 in this quadrant and in this quadrant, because those are the, nope, that's wrong. I was just testing you to see if you're paying attention. Is that quadrant and that quadrant? And is it this first angle of pi 6 or the second angle of pi thirds? Second one, it's at pi thirds. So x could be pi thirds. What about that one down there? What's that? Negative pi thirds or 5 pi thirds, either way. And then how do you account for the fact that you could go around the unit circle more than once? Plus 2 pi n. There you go. So the trick required there to solve that really was knowing the fact that sine of 2x is 2 sine x cosine x, right? Knowing that that was true is what lets you take out the greatest common factor, right? Once you've got that trick, the rest is pretty easy. But that's one thing that I know comes up on some homework problems. I've been looking through the ones I've assigned, and it does like occasionally happen. So if you see a weird trig thing, just Google identities and see if you can figure out which one it is. I probably wouldn't put that on a test. I would give it to you where it was already like this and didn't involve that like memorization step. Okay, so solve these equations. When does sine equal 1/2? So in which quadrants of the unit circle is the sign positive? 1 and 2. Great. And is it the angle of pi 6 or pi thirds? Pi 6 and 5 pi 6. And to account for the fact that you have to go around the unit circle more than once, you say plus 2 pi n. Nope, don't care. It'll only matter in WebAssign if they say to use a specific letter, they'll be looking for that letter. But for me, I don't care. Yeah.
So it doesn't, because I know you said 2 pi r.
That's fine too. Yeah, it doesn't really matter to me as long as you just know that there's a variable and you get 2 pi times something. It probably wouldn't hurt to say n is an integer, but I just don't want to have to be picky about too many little tiddly bits. Does that make sense? Or if you say use r as an integer, don't care.
Ever not?
Not really, right? So n is almost always an integer, so I kind of just like take it for granted that it is. So we just won't worry about it too much.
No, I mean, is it ever not the case where it's not plus 2 pi n?
Occasionally, yes. Like if you're given a restricted interval, and I just say, okay, from negative 2 pi to 2 pi only, then you would just list the ones within the interval. And with certain functions, I think I probably have an example that comes up next, you can actually add pi n. So if I do something smart, this one I think is one of the smart ones. Sine equals cosine. Okay. This you kind of have to solve by inspection on your unit circle and say, okay, when are the x and the y the same? Pi over 4. And also at 5 pi over 4. Now notice that those two angles are equidistant from each other. So to get from pi quarters to 5 pi quarters, how much do you add? Pi. And then to get back to up there, you'd add another pi, right? So in that case, you can actually list it as pi quarters plus pi n, instead of having to have 2. And I might be a bit picky there, and I probably would deduct a little bit of points if you just blindly listed them as plus 2 pi without knowing that you could actually put it into like one compact form. I'm just seeing if you can recognize that, okay, they're equidistant, I can just add pi to get from one to the other.
It's not really quarter pi then, though, if you add 1 pi. You know what I'm saying?
Say that again?
You're not at quarter pi when you go to pi.
No, but it is true at both pi quarters and 5 pi quarters that sine and cosine are equal, right? So if you do pi quarters plus 1 pi, it puts you at 5 pi quarters.
But I'm saying if you did, yeah, but it wouldn't be where but you're saying it's 5 quarters? So you could say 2 pi and still always be correct as long as you said the same statement below, right?
Yes, it would just be not quite as pretty. Does that make sense? Like you could say this, and as long as you added that statement, you haven't missed anything. Does that make sense?
Yeah.
But I would like you to recognize that because these lists have overlap, if there are numbers in this that are, is that fair to say? They don't actually have overlap. Because these two lists can be written more compactly as just that one list. Yes?
On like quiz questions, you always put plus minus.
No, because the fact that it's an integer, it accounts for the plus minus. Because integers can be negative. I don't know if I quite got your question yet, but
Yeah,
does that make sense? Like this is not wrong. It's just that I would like to see that you recognize that this is a little bit better.
It's just like not simplifying.
It's kind of like not simplified. It's a great analogy. It's kind of like it's not simplified all the way. But if you had come out where the two angles that worked were, say, like this angle, and they're not an equal distance apart, then you have to have two separate lists. Does that make sense? That's the difference. It's a little bit subtle, a little bit picky, but that's just something that is like knowing that those can be compacted into a smaller thing.
5 pi.
So that list, the first list that circled includes 5 pi over 4. Does that make sense?
Quicker, yeah.
It's quicker, exactly. Yep.
Okay.
Okay. And these identities you really do have to know, okay? I swear to you, these are important. They're the Pythagorean, and they come from the Pythagorean theorem. Like, it's not that hard. In the unit circle, the hypotenuse is 1. This side is the cosine of your angle, right? This side is the sine of the angle, right? Yes? So, a squared plus b squared is c squared? Yes? Okay, so that's where the first one comes from. The first one is Pythagorean theorem. And I will teach you a trick to memorize the next two. Okay, this is my awesome trick. How do you get secant? You do 1 divided by which function? Cosine. So take this thing, divide by cosine squared. That makes this. Sine squared over cosine squared is tan squared. Okay. Cosine squared over cosine squared is 1. 1 over cosine squared is secant squared.
Oh, that is clever.
Isn't that clever? How do you think you get the other one? Divide by sine squared. And I listed them in the order they are because of making sure it's completely clear. Sine squared over sine squared is 1, right? Cosine squared over sine squared is cotangent squared, right? And 1 over sine squared is cosecant squared. If you can memorize, like, not what they are blindly, but where they come from, that's probably going to be more effective. Personally, I have to re-derive them in my head every time I use them because I can't remember exactly what goes where. The first one, I memorize. The second one, I'm like, okay, I divide by cosine squared, divide by sine squared to get the other. So. I think that's the end of the trig thing, right? Let's take like a 5-minute potty break.